Welcome to the third lecture on inverse trigonometric functions. In the last lecture, we saw some of the identities and relations between some of the inverse trigonometric functions. In this lecture also we will continue to do so and hopefully finish it, and in the subsequent lectures we are going to take up problems. Before we start deriving some new relations, here is a general problem that we are going to face throughout this lecture, and also maybe while solving problems related to inverse trigonometric functions. So, for example, here let us say that we are asked to find a value of x between -1 and 0 such that sine of cos inverse x equals half. So, somebody could try this route. So, somebody could say that okay, half is equal to sine of 30 degrees, which is pi over 6, and then equate cos inverse x with pi over 6. So, he could write cos inverse x is therefore pi by 6, and then taking cos on both the sides here, he would get x equal to cos of pi over 6, which is equal to square root of 3 over 2. The problem is that square root of 3 over 2 does not belong to the interval -1 to 0. So, what do we do in such a case? The thing to be realized here is that if x is between -1 and 0, then from the graph of the cos inverse function you can see that cos inverse of x would belong to the interval pi by 2 to pi. But then the problem is that sine inverse of half. So, if you remember, we said that cos inverse x is equal to, so pi by 6 is sine inverse of half. So, the problem with equating this cos inverse x to sine inverse half is that sine inverse half will always belong to the interval minus pi by 2 to plus pi by 2, and that is because the range set of sine inverse is minus pi by 2 to plus pi by 2. Whereas, if x is in the interval -1 to 0, then cos inverse x will belong to another interval pi by 2 to pi, and we see that this interval and the range set of sine inverse are mutually exclusive. So, the intersection of these two is the null set, and therefore, we end up with the problem that we got a value of x which does not lie in this interval. So, we will be facing similar, this is the basic pattern of the problem that we might face. So, the solution out of this is that, again going back to the example. So, obviously, if x is between -1 and 0, then cos inverse x, which I denote by theta, will definitely lie between pi by 2 and pi. And then instead of going and straight away saying that cos inverse is sine inverse of half, which is not possible because sine inverse of half will not belong to this set. So, cos inverse x cannot be equal to sine inverse half. But then we see that sine of pi minus theta is the same as sine theta, and therefore, we can. So, the reason why we took this choice of pi minus theta is because if theta equal to cos inverse x belongs to this interval, then we will see that pi minus theta, if theta belongs to this interval, then pi minus theta belongs to the interval 0 to pi by 2. So, and this interval 0 to pi by 2 now that we get belongs to the range set of sine inverse. So, this is the basic trick that has to be done, and of course, we know that. So, this sine theta is actually sine of cos inverse x, and that is given to be in the problem, this value is given to be half. So, what we have is sine of pi minus theta equals to half, and then obviously we can say that pi minus theta equals sine inverse of half. The reason why, so from here we can conclude this line only because this pi minus theta belongs to the range set of sine inverse. So, pi minus theta belongs to 0 to pi by 2, which is a subset of the range set of sine inverse. The range set of sine inverse was minus pi by 2 to pi by 2. So, because of the fact that pi minus theta belongs to the range set of sine inverse, from here we can get this. And this basically then means is that since theta is cos inverse of x, so what we get is pi minus cos inverse x is sine inverse of half. Of course, sine inverse of half equals pi by 6, and therefore we get cos inverse x equals pi minus pi by 6, which is 5 pi over 6, and therefore x is equal to, now if we take the cos on both the left and the right hand side, we get x equal to cos of 5 pi by 6, which is going to be equal to minus cos pi over 6, which is equal to minus square root of 3 over 2. So, finally, we get x equal to minus square root of 3 over 2, which belongs to this interval minus 1 to 0. So, this is the correct solution. So, the essential, the main point here was that if we directly try to substitute cos inverse x as equal to sine inverse of half, then we get into a problem, because the sine inverse of half belongs to the range of sine inverse, which is minus pi by 2 to plus pi by 2, whereas for x negative, cos inverse of x does not belong to the range. So, essentially if we equate it like this, then for sure the value of x that you get here is not going to lie in the interval minus 1 to 0. So, we can formalize this thing in the next slide. I have tried to formalize this. So, the essential problem is that, suppose that f is a trigonometric function of the form, it could be any of these 6 trigonometric functions that we have defined. So, in general, the trigonometric function has a domain A and a range B, and then we went on to defining the inverse of each of these 6 trigonometric functions. So, the inverse function f inverse, obviously the domain set is going to be the same as the range set of the function f, which is B. So, the domain of f inverse is the set B, and the range set will be another set C, which of course has to be a subset of the set A, which is the domain of the function f. So, the general problem is that, suppose if we are said that we have to solve this equation where we have to find theta. So, the value of x is given and we have to find theta such that f of theta equals x. Now, we are already said that theta belongs to the range set of f inverse, then the solution is very easy. The solution is simply theta equal to f inverse of x, because f inverse of x will belong to the range set of f inverse, which is C. Therefore, theta will definitely belong to. So, if we say that theta has to belong to C, then this solution satisfies this constraint that theta has to belong to the range set of f inverse. But if let us say that we have the same problem, f theta equal to x, we have to find theta, but it is said that we need to find a value of theta which does not belong to the range set of f inverse. Then the question is, how do we find theta now? Obviously, theta cannot be equal to. So, in this case where we are said that theta does not belong to the range set of f inverse, it is clear that theta is not equal to f inverse of x, because f inverse of x will always belong to the set C, whereas it is clearly mentioned here that theta must not belong to the set C. So, how do we find theta in such a case? So, I have tried to solve this problem in general for the sine function. So, for the sine function, the domain and the range is as written here, and for the sine inverse function the domain is -1 to 1, the range is -π/2 to +π/2, and let us say that we have to solve this equation here. So, we have to find the theta such that sin theta equal to x, x of course belongs to -1 to +1. So, we have to find theta, but what we are given is that theta belongs to this range. So, where m is some integer. So, this is what we are asked to find. We are asked to find a theta which belongs to this range m pi minus π/2 to m pi plus π/2 to this interval, such a way that sin theta is equal to x. So, how do we find it? So, this is not very tough. Of course, we need to consider even and odd m. So let us say that if so we start with writing this equation sin theta equals x, and we are said that theta belongs to this interval, but the problem is that of course if we take the special case of m equal to 0, then what this basically this constraint over here translates to theta belonging to -π/2 to +π/2, and this is the range set of sine inverse, and therefore, for the special case of m equal to 0, the solution is very easy, theta equals to sine inverse x. So, this is the solution for m equal to 0, because for m equal to 0, this set where we are constraining theta to lie in will essentially become the range set of sine inverse. But what if m is not equal to 0? So, in the case where m not equal to 0, we will have to do something more. So, we again start with sin theta equal to x, and we are said that theta belongs to m pi minus π/2 to m pi plus π/2, the closed interval. But what we see is that theta minus m pi, if theta belongs to this interval, then theta minus m pi belongs to the interval minus π/2 to plus π/2, which, and this interval is basically the range set of sine inverse. Now, let us see what is the value of sine of theta minus m pi, and we will see that this is equal to sin A cos B minus cos A sin B, but sine of an integer multiple of pi is equal to 0. So, this is what we end up getting, and this cos of m pi can be written as -1 to the power of m. So, this is equal to finally equal to -1 to the power m times sin theta, which is actually good news for us, because we can also write it as -1 to the power of m times x, because sin theta is equal to x. So, then we can divide this into two cases. One is when m is even. So, when m is even, this equation essentially becomes sine of theta minus m pi equals x, and then if we see here, this theta minus m pi obviously belongs to the range set of sine inverse, and therefore, from this equation we can directly write that theta minus m pi equals sine inverse of x, from where we can conclude that theta is equal to m pi plus sine inverse of x. So, in the case where m is even, this is the solution. So, and then for the case of odd m, it is going to be similar. For odd m, what we are going to see is that sine of theta minus m pi equal to -1 to the power m times x is simply minus of x, and we already know that this theta minus m pi belongs to the range set of sine inverse, and therefore, from this statement we can directly say that theta minus m pi is equal to sine inverse of minus x, but sine inverse is an odd function, and therefore, this is equal to minus of sine inverse x, from where we finally conclude that when m is odd, theta equals to m pi minus sine inverse x. So, this whole thing can be summarized as in the following slide here. So, the basic problem was to find a theta in this interval m pi minus pi by 2 to m pi plus pi by 2, where m is some integer, and we have to find this theta in this interval, and theta should be such that sin theta is equal to some value x. So, the general solution for that is, if m is even, then theta equals m pi plus sin inverse x. If m is odd, then it is m pi minus sin inverse x. Similar kind of equations can be derived for the other trigonometric functions also. We now move over to the problem, or to the identity which we had where we had stopped in the previous lecture. So, if you remember, we were trying to see if tan inverse of x plus tan inverse of y can be written as tan inverse of something. So, here is a quick derivation. So, tan of, we know that tan of a plus b equals tan a plus tan b over 1 minus tan a tan b. Now, in this formula here, if I substitute a equal to tan inverse of x and b equal to tan inverse of y, then this is what I get. So, tan of this is a and this is b. So, tan of a plus b is tan a plus tan b divided by 1 minus tan a times tan b. And of course, tan of tan inverse x is x, tan of tan inverse y equals y, and therefore, this is what we get. So, ultimately what we get is tan of the sum of tan inverses of x and y is simply equal to x plus y over 1 minus x y. So, we have this statement here. But does this necessarily imply that tan inverse x plus tan inverse y equals tan inverse x plus y over 1 minus x y? Is this always true? The answer is no. It depends on the values of x and y, because we know that the range set of the tan inverse function, the range set is minus pi by 2 to plus pi by 2. So, therefore, if x and y are such that tan inverse x plus tan inverse y, if it does not belong to the range set of tan inverse, then we cannot have this equality here. So, that is the problem. So, in the next few slides, I will derive the following result. So, here is a nice table. So, if we will show that if x times y is less than 1, then it is true that tan inverse x plus tan inverse y is exactly equal to tan inverse x plus y over 1 minus x y. But so, this is equal to this only if x y is less than 1. But for the other cases, so the other case is if both x and y are positive and x y is greater than 1. In that case, we will have to add a pi to this expression. So, this is what we get. On the other hand, if both x and y are negative, but the product is still greater than 1, we add a minus pi. So, to show these three conditions, we will need a small result, which is something that we have already seen in the previous lecture, but I still thought of writing it down here. So, from the previous lectures, we have seen both these properties. So, one was that for any x real, this sum of tan inverse and cot inverse x is pi by 2 always, and also that if x is positive, then tan inverse 1 over x is the same as cot inverse x. So, now if we try to combine both these statements, so then we can write that for x non-negative, we just replace this cot inverse x over here is replaced by tan inverse 1 over x. So, then we get this particular equation, which is that for all x non-negative, tan inverse x plus tan inverse 1 over x is always pi by 2. And then if we multiply this whole thing by a minus sign, we get minus tan inverse x minus tan inverse 1 over x is minus pi by 2 for all x greater than 0. But since the tan inverse function is an odd function, we can write minus of tan inverse x as tan inverse of minus x, and the same for this term here. So, then this is what we end up getting, but the condition x greater than 0 can also be written as minus x less than 0. So, now we see that in this equation we have minus x everywhere. So, if we use another variable y equal to minus x, then the same thing can be written as tan inverse y plus tan inverse 1 over y is minus pi by 2 for all negative y. So, we will probably just be using this and these two equations, which look very similar except that we have pi by 2 and minus pi by 2 here. So, let us take the case of x y when the product of x times y is equal to less than 1. So, when x times y is less than 1, but both x and y are positive. So, since x and y are both positive, tan inverse x will belong to the interval 0 to pi by 2, and that is clear from this graph of tan inverse x. So, if we just look at the for positive values of x, so for these values of x we see that the tan inverse x is taking values on the positive side of the vertical axis. So, that is why when when x is greater than 0, then tan inverse x will belong to this interval from 0 to pi by 2, and the same is true for tan inverse y. So, tan inverse y, because y is positive, tan inverse y will also belong to 0 to pi by 2. But we also have this third condition that x y is less than 1. So, that basically means that y is less than 1 over x, but both y and 1 over x are positive because x and y are positive. So, we have this thing here. So, we will try to focus only on the positive x axis of this curve. Now, you see that on the positive side of the horizontal axis, the graph of tan inverse x is monotonically increasing, and therefore, from here we can say that tan inverse y is less than tan inverse 1 over x. Now, we add tan inverse x on both the sides. So, what we get is, and of course, so then what we get is, of course, we have a greater than 0 sign over here, and we also know that tan inverse x is greater than 0 because both x and y are positive. Now, to this equation here, we will add tan inverse x everywhere. So, what we will get is tan inverse x plus 0 is tan inverse x is less than tan inverse x plus tan inverse y, and that is less than tan inverse x plus tan inverse 1 over x, and of course, tan inverse x here is greater than 0. So, what we saw from the previous slide is that for all x positive, tan inverse x plus tan inverse 1 over x is actually equal to pi by 2, and therefore, we clearly see that if x and y satisfy this condition, then tan inverse x plus tan inverse y, which is here, is positive and it is less than pi by 2. So, essentially for this when x and y satisfy this condition, then the value of tan inverse x plus tan inverse y belongs to the range set of tan inverse, and therefore, because they belong to the range set of tan inverse, what will happen is that tan inverse x plus tan inverse y will be equal to this. Of course, the other condition is that if xy is less than 1 and both x and y are negative, and this can also be for this case also the result is very similar, that tan inverse x and tan inverse y, since x and y are negative, will both belong to the interval minus pi by 2 to 0. And in this case, from here what will follow is y is greater than 1 over x, because both x and y are negative. Therefore, from here we get this condition. And then from this condition, so now we are basically on the negative side of the horizontal axis. So we get tan inverse y is greater than tan inverse 1 over x, because the tan inverse function is monotonically increasing with x, as can be seen from this graph here. And because x is and then from this, if we add tan inverse x to both the sides, this of course is less than 0, and tan inverse x is also less than 0. So if we add tan inverse x to this particular inequality, what we get is tan inverse x is greater than tan inverse x plus tan inverse y is greater than tan inverse x plus tan inverse 1 over x. And this tan inverse x is obviously negative. So from here we also see that now on the previous slide we saw that for all x negative, tan inverse x plus tan inverse 1 over x is equal to minus pi by 2. And therefore, it follows that if x and y satisfy these three conditions, then tan inverse x plus tan inverse y lies between 0 and minus pi by 2, and this interval 0 and if x and y satisfy this condition, then tan inverse x plus tan inverse y belongs to the interval minus pi by 2 to 0, which is a subset of the range set of tan inverse. So even for this case, so this case is also a subset of this case. So essentially both, so this is case 3. So both case 1 and case 3 belong to this particular case, because if you remember, case 1 was also x y less than 1, but both x and y positive, and case 3, which we discussed just now, is also x y less than 1, but here both x and y are negative. So both these cases belong to this condition here, and in both cases we saw that we showed that tan inverse x plus tan inverse y belongs to the interval minus pi by 2 to plus pi by 2, which happens to be the range set of tan inverse, and therefore this will be equal to this. So one more case which remains, if we go back to our table that we saw just now. So we have actually divided this x y less than condition into three. Basically we first divided into two different conditions. So one condition is that x y is less than 1, but it is greater than 0. So this case 1 and case 3, which we just saw now, are basically for this sub condition, and then there is another condition which is x y is less than or equal to 0. So if we take the union of this and this condition, we finally get this condition. Now for this condition, we have already shown case 1 and case 3 before. Now we are going to show that tan inverse x plus tan inverse y is equal to this also when x y is non-positive. So if it is less than or equal to 0. So that will prove that for this condition x y less than 1, tan inverse x plus tan inverse y is equal to tan inverse of x plus y over 1 minus x y. So we have named it as case 5. So I will write, so this I will write as case 5 here. So when this is quite easy, because when x and y is non-positive, so one case is that x is less than or equal to 0, y greater than 0, y greater than or equal to 0. The other is the opposite. x is greater than equal to 0, but y is less than equal to 0. So, for case 5a, because x is less than equal to 0, we see that tan inverse x will belong to the interval minus pi by 2 to 0, and tan inverse y will belong to 0 to pi by 2. And then of course, since we add tan inverse x with tan inverse y from this and this, it follows that tan inverse x plus tan inverse y will belong to the interval minus pi by 2 to plus pi by 2. So, it is very easy to see that for this case, tan inverse x plus tan inverse y will belong to, this is the range set of tan inverse. And again, when x is greater than equal to 0 and y is less than equal to 0, tan inverse x will belong to 0 to pi by 2, tan inverse y will belong to minus pi by 2 to 0. So, even in this case, you will see that tan inverse x plus tan inverse y will belong to the range set of tan inverse. And that is because if you see 0 to pi by 2 and minus pi by 2 to 0 are if you take when we add these two, we essentially have to take the union of this set with this set, and the union is precisely the range set of tan inverse, and the same thing is happening in this case also. So, essentially we have shown the first row here. So, this was case 5. So, the union of this and this is this condition x y less than 1. So, what we have shown is that if the product of x and y is less than 1, then tan inverse x plus tan inverse y belongs to the range set of tan inverse, and therefore, it is equal to this expression here. The other two cases are also not very difficult. So, one case is where x y is greater than 1 and both x and y are positive. So, in this case, tan inverse x will belong to 0 to pi by 2, tan inverse y will belong to 0 to pi by 2 again, because both of them are positive, and because x y is greater than 1, we have y greater than 1 over x. So, since tan inverse is a monotonically increasing function, from here we get this statement that tan inverse y is greater than tan inverse of 1 over x. And then, as we did before, we will add tan inverse x on both the sides, and this is what we end up getting. So, on the right hand side, we again get tan inverse x with tan inverse 1 with tan inverse x plus tan inverse 1 over x, which we had shown that when x is positive, the value of this is equal to pi by 2, and therefore, what we see is that for this scenario here, tan inverse x plus tan inverse y is actually greater than pi by 2. It is greater than pi by 2, and therefore, for this case what we have is, so let us say if I say theta is tan inverse x plus tan inverse y. So, this is for the case number 2. So, what we have is this is greater than pi by 2, but of course, this theta has to be less than pi because tan inverse x and tan inverse y both have belong to 0 to pi by 2. So, the largest positive value of tan inverse x plus tan inverse y can only be pi by 2 plus pi by 2, which is pi. So, obviously, this theta has to be less than pi. So, ultimately for this case too, what we have is that theta belongs to the interval pi by 2 to pi. The problem now is that, of course, tan of this theta is equal to x plus y over 1 minus x y. So, this follows from our very first slide on the tan inverse functions in this lecture. So, the basic problem is again that we are given that, so this is we are given that theta must belong to the interval pi by 2 to pi, and at the same time it should satisfy this condition, this equation that tan theta is equal to x plus y over 1 minus x y. So, if you remember, this again is a problem of the type that we were discussing in the first few slides, that you have f of theta. So, here f is the tan function equal to some z. So, z is basically this value, and we need, but the problem is that this theta doesn't belong. So, theta doesn't belong to the range set of f inverse. So, even here we see that theta actually belongs to the interval pi by 2 to pi, which is not the range set of f inverse. The range set of tan inverse is actually minus pi by 2 to plus pi by 2. So, this is exactly the type of the pattern of problem that we were discussing in the first few slides, and you will keep encountering, or you will keep seeing this type of problem whenever you deal with inverse trigonometric functions. So, in this case the trick that we do is, first of all we see that since this is not the range set of the tan inverse function, we need to do something so that some operation on theta, so that we basically have so what we do is we take this theta and we actually subtract pi from it. So, if we subtract pi from it, then because theta belongs to pi by 2 to pi, what will happen is that theta minus pi will belong to the interval minus pi by 2 to 0. And what we know is that minus pi by 2 to 0 obviously belongs to. So, this interval is a subset of the range set of tan inverse. And the reason why, so the reason for subtracting pi from this theta is twofold. The first reason is that I get a new angle theta minus pi which belongs to the, so this belongs, so this interval is a subset of the range set of tan inverse. So, the reason for subtracting pi is twofold again. The first reason is that I get a new angle theta minus pi which belongs to the range set of tan inverse. The second is that I know that the tan function is periodic with pi. So, tan of theta minus pi is the same as tan theta, which we know is equal to x plus y over 1 minus x y. So, that is the other reason why we chose this angle pi to be subtracted from theta. So, at the end what we have in this equation here is that we have tangent of an angle where this angle belongs to the range set of tan inverse equal to this value x plus y over 1 minus x y. And therefore, now we can easily write that theta minus pi is equal to tan inverse of x plus y over 1 minus x y. And then from here it follows that theta equal to pi plus tan inverse x plus y over 1 minus x y, and that is what was exactly written in the table here, that so this was case number 2. So, if x and y are both positive and x y is greater than 1, then tan inverse x plus tan inverse y will be equal to pi plus tan inverse of x plus y over 1 minus x y. So, that is what we had just proved now, and in the interest of time we will not go ahead with the proof of this last statement, but that can also be done exactly in a similar way that we did case 2. And then of course, from tan inverse x plus y, it is very easy to derive expressions for example 2 tan inverse, because we can write 2 times tan inverse as tan inverse x plus tan inverse x, and then we can use the tan inverse x plus tan inverse y formula with y equal to x, and this is what we are going to get in that case. So, you can it's basically going to be a little exercise for you to verify this. Again, from the tan inverse x plus tan inverse y, it is easy to get the expression for tan inverse x minus tan inverse y, and I will quickly go through it. So, tan inverse x minus tan inverse y can be written as tan inverse x plus tan inverse of minus y, and that is because the tan inverse function is an odd function. And then we will, so now that we have written it this thing as a sum of the tan inverses of 2 different variables x and minus y. So, we should be able to use our result that we had earlier, if we use that table, then what we see is that we had these three conditions. One was, so the first condition is x times minus y less than 1. So let me show you that table very quickly. So it's very simple. What we have to just do is that in this whole table, everywhere we have to just replace this y by minus y, and then we'll get the expression for tan inverse x minus tan inverse y. So that is what we have done here. So if you replace y with minus y in that table, this is what you get. So x times minus y. So earlier we had x y less than 1, but we replace y with minus y. So we get x times minus y less than 1, which can be written x. The same condition can be equivalently written as x y is greater than minus 1. And then we had earlier we had on the previous slide tan inverse x plus y, but then instead of y we write minus y. So we get x plus minus y over 1 minus x y is what we had earlier, but because y gets replaced with minus y, what we have now is 1 minus x times minus y. And the same thing we have to keep on doing for the other conditions. And so finally we end up getting, so these three are the rows for the conditions and the values for tan inverse x minus tan inverse y, depending on the condition satisfied by both x and y. So far we have only seen how to add the tan inverse of two different variables x and y, but of course these things can be generalized to, for example, let us say that we want to compute sin inverse x plus cos inverse y. And how do we do it? So one method could be that we can obviously find out conversion formulas from sin inverse x to tan inverse of something, and again from cos inverse y to tan inverse of something. So essentially we convert both these terms here to tan inverses of two other variables, and then since we already know from the previous slide as to how to add the tan inverse of two variables, we can get this whole thing as a tan inverse of one variable, and then that should help us. So the problem is that for doing that we would need some conversion formulas from sin inverse to tan inverse and vice versa, and then from cos inverse to tan inverse, and then from tan inverse to cos inverse. So in the following slides we will try to quickly go over them. So let us take the case of sin inverse and tan inverse. So the question here is that we are having a value of x which obviously is between minus 1 and plus 1, and then we want to see sin inverse of x is equal to tan inverse of what. So we want to find this question mark here. So let us say that theta is equal to sin inverse x, then obviously theta belongs to the range set of sin inverse, which is minus pi by 2 to plus pi by 2. And then since we want to find this unknown thing here, we are interested actually in finding tan of sin inverse x, because if you see this equation here, if I take the tangent function on both the sides, what I will end up getting is tan of sin inverse x, if I take the tan on both the sides, is equal to this unknown thing here. So, and since sin inverse x is denoted by theta, we eventually want to find tan of theta. But tan of theta is sin theta over cos theta. From here we already see that sin theta is actually equal to x, and cos theta is easy to find out because in this case, because theta belongs to minus pi by 2 to plus pi by 2, cos theta will always be positive, it will always be positive, and therefore and also that we already know this formula that cos square theta is equal to 1 minus sin square theta. Sin theta is x, so we can write cos square theta as 1 minus x square, and then of course cos theta is equal to the positive square root of 1 minus x square, because we know that when theta belongs to this interval, cos theta is greater than 0. So we take the positive square root of 1 minus x square, and that is what we put in here. So, therefore, we finally get that tan of theta is equal to x over root of 1 minus x square. And so, if you want to write it cleanly, we can write it as tan of sine inverse x equals x over root of 1 minus x square. And because now this, if you see this sine inverse x will obviously belong to this interval, and this interval also happens to be the range set of tan inverse. So, we have tan of some angle theta equals this value, and this theta belongs to the range set of tan inverse, and therefore, it is very easy to see that obviously this theta will be equal to tan inverse of x over root of 1 minus x square. So, this question mark over here is precisely equal to x over root of 1 minus x square. And then we have to do the reverse also, which is that suppose if we are given some value of x belonging to real numbers, and then we are asked this question that find this argument of the sine inverse function such that tan inverse x is equal to sine inverse of this unknown variable here. So, again we start in a similar manner as what we did earlier. Let us denote tan inverse x by theta. Then obviously theta belongs to the range set of tan inverse, which is the open interval from minus pi by 2 to plus pi by 2, and then sine theta can be written as tan theta over secant theta, because secant theta is 1 over cos theta, which is equal to tan theta over the square root of 1 plus tan square theta. So, we know this identity that 1 plus tan square theta is sec square theta. So, this is what we have used for this step over here. So, then we can write, since theta is defined like this, it is obvious that x is actually equal to tan theta. So, we replace this tan theta by x here, and then tan square theta will get replaced by x square obviously. This square root here is a positive square root. The reason being that when theta belongs to the interval minus pi by 2 to plus pi by 2, cos theta and therefore secant of theta is positive for all theta in this interval, and therefore, since secant theta is positive, we will take the positive square root of 1 plus x square. So, finally, what we have is that sine of theta, where theta is tan inverse x, is equal to this. So, we can actually write it as sine of tan inverse x equals x over root of 1 plus x square, but this angle tan inverse x belongs to minus pi by 2 to plus pi by 2, which is also the range set of sine inverse. It is, so this is actually a subset of the range set of sine inverse, and therefore, from this statement here it follows that tan inverse x is equal to sine inverse of x over root of 1 plus x square. So, this big question mark here inside the argument of the sine inverse function is actually equal to x over root of 1 plus x square. A little example would help us to realize the importance of these formulas that we just derived now. So, let us say that we are asked to compute the value of sine inverse of 1 over 3 plus sine inverse of this other real number, which is 2 by 3 times 1 minus square root of 1 minus 1 over square root of 8. So, if we remember, we just proved this formula that sine inverse of x equals tan inverse of x over root of 1 minus x square. So, with x equal to 1 over 3, and if we use this formula, then what we will end up getting is sine inverse of 1 over 3 is equal to tan inverse of 1 over 3 divided by square root of 1 minus 1 by 9, because 1 over 3 whole square is 1 by 9, and then this will be equal to tan inverse of 1 by square root of 8. So, sine inverse of 1 over 3 is actually tan inverse of 1 over square root of 8, and this is the positive square root. If we go back, you recollect that we had taken the positive square root here. And similarly, for the other term also, we can write that sine inverse of 2 by 3 times 1 minus 1 over square root of 8 equals tan inverse of, so this is x, so 2 by 3 times 1 minus 1 over square root of 8 divided by the positive square root of 1 minus the square of this thing, which will be 4 by 9 times 1 minus 1 by square root of 8 whole square, and that can be simplified to tan inverse 2 into 1 minus root 8. So, we will take this 3 down into the square root. So, that becomes 9 minus 4 times the square of this particular term here, which will be 1 plus 1 by 8 minus 2 by square root of 8. And that, if we take it to the next slide, will be equal to tan inverse of 2 times 1 minus 1 by square root of 8 over square root of, so 5 and then minus half and then plus 8 by square root of 8, which is equal to tan inverse of 2 times 1 minus. So, we can actually take the square root of 8 down and see what we get. So, well, this can be also written as 2 times 1 minus 1 over square root of 8 over square root of 9 by 2 plus square root of 8, and that is equal to tan inverse of 2 into square root of 8 minus 1 by square root of, so we take the square root of 8 to the denominator here, we get 36 plus 8 times square root of 8. So, that will be 8 times square root of 8. So, this is for the other term. So, this particular term here, sine inverse of 2 by 3 times this is equal to tan inverse of this thing. And then, so now we have to, so we earlier saw that sine inverse of 1 over 3 was calculated to be tan inverse of 1 over root 8, and we got another expression for this thing, which is here. So, now we should be in a position to add both of them. So, finally, what we have is that sine inverse of 1 over 3 plus sine inverse of 2 by 3 times 1 minus 1 over square root of 8 is equal to tan inverse 1 over square root of 8 plus tan inverse. So, in this expression we can cancel this 4 with we can take square root of 4 here. So, we get square root of 8 minus 1 by square root of 9 plus 2 times square root of 8. So, now what we have done essentially is we have converted the sum of 2 sine inverses into the sum of 2 tan inverses, and then we use the tan inverse x plus tan inverse y formula. So, in this case what you can check, and that I will not do now, is that, so we have x equal to this value and y equal to this value, and you can check that the product of this x and this y is less than 1. So, that means that I can use for tan inverse x plus tan inverse y, I can use this formula tan inverse x plus y by 1 minus xy. This is because this times this, which is x times y, is less than 1. And then it becomes very easy, because then we can write it as tan inverse of 1 by square root of 8 plus root 8 minus 1 by root of 9 plus 2 root 8 over 1 minus, and then 1 by square root of 8. So, it becomes minus root of 72 plus 2 times, so plus 16 times square root of 8. And this upon further simplification, whatever is inside here will be 1 actually. So, the numerator and denominator will be the same, and that is left as an easy exercise. So, this will become tan inverse of 1, which is equal to pi by 4. So, in this lecture we essentially derived some more relations between these inverse trigonometric functions, and specifically we discussed the formula for tan inverse x plus tan inverse y, and the conversion between sine inverse and tan inverse. So, in the next class we will see some other formulas and take up some problems also. Another very important thing which we also saw in this lecture is that we showed how to deal with the cases where we have f theta equal to x, where f is some trigonometric function, but theta is constrained to be not in the range set of f inverse. Thank you.